Hi, my name is Heather Hansen, and I'm a third-year PhD student at The Ohio State University. I'm going to start with a brief overview of my poster, and then if you're interested, I'll go into some more detail afterwards. Okay, so I'm broadly interested in the emotional processing of sensory stimuli, specifically in the connections between the amygdala and the ventral visual cortex, and how this connectivity changes across development. So in this project, we looked at the functional connectivity between these regions in samples of adults and neonates. First, to the entire anatomical cortex of the occipital and temporal lobes, and then to the functional parcels located within that cortex. So in the anatomical analysis, shown at the top in green, we saw that adults, in gray, have a gradient-like pattern of decreasing connectivity, whereas neonates, in red, are largely undifferentiated. In the functional analysis, depicted on the bottom in teal, results revealed increased connectivity in adults to higher level sensory processing regions, such as those that process faces or objects, and minimal connectivity to primary sensory regions. Overall, adults showed specialized connectivity between the amygdala and the occipitotemporal cortex, whereas neonates do not. Thus, it would suggest that the specialization of this cortex is not present at birth and is at least somewhat dependent on experience. All right, thanks for listening. If you have any questions, I'm now going to do this again, but more in detail. Okay, so previous work in adult macaques has shown that specific subnuclei of the amygdala, specifically lateral and basal, which process sensory information, connect to the ventral visual cortex on a gradient, which you can see here in the diagram. Adults show stronger anterior connections, and the connections decrease on a gradient as you move posterior. Infants show similar connections, but do undergo refinement, specifically in the posterior visual areas. So we wanted to ask, does this gradient-like connectivity pattern exist in humans? Does it differ across development? And perhaps more interestingly, what functional regions exist in these areas that might lead to these connectivity differences? So to answer this, we used 40 adults from the Human Connectome Project and 40 neonates scanned within 1 week of birth from the Developing Human Connectome Project. We made sure to match the samples for motion and sex to limit confounds. Now to start, I anatomically defined the amygdala subnuclei of interest, specifically the basolateral amygdala, natively in each subject using automated segmentation. To address the first question, the anatomical gradient, I split the occipitotemporal cortex, or OTC for short, into 5 equal sections from anterior, section 5 in blue, to posterior, section 1 in green, in each individual subject. I then calculated the functional connectivity between the basolateral amygdala and each of these 5 sections. Here on the right, you can see the average connectivity to the 5 sections on the x-axis of this bar graph, and functional connectivity on the y-axis, with adults in gray and neonates in red. Now, adults display decreasing functional connectivity moving from anterior to posterior, whereas neonates are largely undifferentiated. The connectivity differences between these two samples is also evident on the spider plot on the right, because the z-scored connectivity values for adults and neonates show visually different patterns. So in sum, the anatomical gradient also appears in human adults, and the topographical organization is not present at birth. Now, we further asked why this might be the case by exploring the functional regions that live in this cortex. We used a variety of functional parcels associated with primary and higher level visual and auditory processing. Now, since obviously these areas cannot be functionally defined in a neonate, we used parcels that were defined in CVS average space and overlaid each of these parcels onto each subject using ANTs, or advanced normalization tools. You can see the 11 regions we chose on the left, color-coded on these inflated brains. So then we calculated the functional connectivity between the basolateral amygdala and these 11 parcels, split for convenience on the graph into the OTC section they fall in, from anterior on the left to posterior on the right. Now, if the gradient we saw before was independent of function, this graph should effectively match the anatomical analysis, with the highest connectivity to the anterior parcels and decreasing connectivity as you move posterior. However, this is not the case. In neonates, we again find no differentiation, but adults show variability between the parcels independent of location. For instance, adults show very minimal connectivity between the amygdala and primary auditory cortex A1, and much stronger connectivity to secondary auditory cortex in the superior temporal gyrus, STG. To see if this pattern of connectivity could be better attributed to the actual function of the parcel, we split the parcels into categories, such as faces, which is comprised of the fusiform face area, FFA, the occipital face area, OFA, and the superior temporal sulcus, STS, etc. And we reran our functional connectivity analysis between the amygdala and these 7 categories instead. Again, no differences between functional categories in neonates, whereas adults show higher connectivity between the amygdala and between faces, bodies, objects, and higher level auditory regions, whereas they show weaker connectivity between the amygdala and scenes in primary auditory and visual regions. Now the spider plot shows which parcels made up each category, and again visually depicts the vastly different connectivity patterns between adults in gray and neonates in red. So overall, our anatomical analyses revealed a gradient of connectivity from anterior to posterior, like in macaques, but no differentiation in neonates. Our functional analyses showed that adults had stronger connectivity to higher level functional regions and weaker connectivity to primary functional regions, whereas neonates showed similar connectivity across all functional regions. Thus, our results suggest that functional connectivity between the amygdala and the occipitotemporal cortex is largely undifferentiated at birth, thus requiring experience to specialize into these functional regions. So thanks for listening and thanks for coming to my poster. Feel free to email me if you have any questions.